Let's look at some examples now. Let's try to solve this differential equation, y double prime plus 6y prime plus 9y equals 0. This is a second order, linear, homogeneous, constant coefficient differential equation. And guess what? The characteristic equation, which is r squared plus 6r plus 9 equals 0, it's easily seen that this factors into r plus 3 squared equals 0. In other words, r equals minus 3 is a repeated root of this polynomial, of this quadratic polynomial. So this is the only solution to this characteristic equation. What does that tell us? This tells us that the function y1 of t equals e to the minus 3t is a solution. We've known that for quite a while at this point. But based on the work we did in the earlier video, we know that y2 of t equals t e to the minus 3t is also a solution. And we already checked this in general, but you could check it again. Here, the Wronskian of these two functions will be non-zero, so that y1 and y2 constitute a fundamental set of solutions. That means the general solution is y of t equals some constant times y1, e to the minus 3t, plus some constant times t e to the minus 3t. So here's our general solution. I think I've written the constants backwards from the way I wrote it before, but it's the same set of functions. I want us to look real quickly at what these solutions look like. I've just picked some examples for the constants here. I picked C1 as -2 and C2 as 1. That's with the C1 and C2 as I've written them here in this representation. And so I've graphed this function here. You see how it behaves. As t goes to infinity, of course, the e to the minus 3t goes to 0, and it goes to 0 very quickly. Even though this t, multiplying the e to the minus 3t, the t gets very big, one can see easily using L'Hopital's rule that t times e to the minus 3t tends to 0 as t goes to infinity. The t grows much more slowly than the e to the minus 3t tends to 0. So the solutions, as you can see here, will tend to 0 as t goes to infinity. Before that, however, depending on the values of these constants, you can have something like this, where the solution starts positive. In fact, in this, what have we done here? We've chosen this solution so that y of 0 equals 1, and y prime of 0, you can see easily, here will be, what is y prime of 0? Let's check here. Y prime of t is minus 2t times minus 3 e to the minus 3t, minus 2 times e to the minus 3t, and then we have minus 3 e to the minus 3t. So y prime of 0, when I plug in 0, will actually give me -5. So you can see how it's going downward very rapidly at 0, even though y of 0 is 1. And you can see that that solution actually goes down below the x-axis and then, of course, tends to 0 as t goes to infinity. Depending on the constants there, you might get a solution that is just uniformly always decreasing to 0 very quickly like that. Of course, it could be increasing to 0 very quickly like that, or you could get a crossing of the axis. It could go up and then down like that. But you're going to get at most one such place where it crosses the axis, because you can easily factor out a linear term times the e to the minus 3t here and see that you'll get at most one place where you cross the x-axis where y is 0. So in general, the solutions kind of look just like the situation where you have two distinct roots if both of those roots are negative, because you'll get exponential functions that die out quickly, and your solutions will all die out, meaning go to 0 very quickly in this situation. The reason they die out is because the root of the characteristic equation, in this case -3, was a negative number. If we look at this example now, you'll see this has characteristic equation r squared minus 2r plus 1 equals 0, easily seen to be r minus 1 squared equals 0, or r equals 1. That tells you y equals e to the t is a solution, which is very easy to check. And by the way, I didn't mention it last time, but you should have checked that those solutions were all valid. And I'll call this function, I'll call this one y2, I think, because I called y1 of t, t e to the t. This is also a solution. And just as before, you'll get two solutions that constitute a fundamental set of solutions, so that just as before, the set of all linear combinations of those solutions is in fact the general solution. And again, we can ask, what do these solutions look like? Well, again, I've chosen here if C1 is -2 and C2 is 1, you get a function that looks like minus 2t e to the t plus, oh, that should be e to the t. I don't know why it says e to the minus t. It should be e to the t there. And you'll see the e to the t as well as the t e to the t both blow up, but the minus 2 e to the t blows up much faster than e to the t's, and because it has a negative sign, that means your solution will tend to minus infinity, and in fact tend to minus infinity very quickly. If you run t in the opposite direction, you'll see that the solutions approach 0 as t goes off to minus infinity. The solutions will very quickly get close to the x-axis there. But to the right, you'll have solutions blowing up either in the upwards direction or the downwards direction, depending on the sign. In fact, in this case, of the t e to the t term, which is the one that will dominate the e to the t term. You would have other solutions that look just like this, that just blow up and stay positive the whole time if both coefficients are positive. Or you could have solutions that just blow up in the negative direction entirely, or you could have solutions that cross the axis at most once. There are many different possibilities.